Okay, can you all hear me okay?
Yeah, we can hear you.
Okay, all right, good. So I've been having some problems with Zoom freezing. So let me know if I freeze. I'm frozen already. Hold on a sec. Oh, there we go. Okay, I just appeared out of nowhere.
You're just teleporting around.
Yeah, I'm just teleporting. Okay. Do you guys have any questions? Do you have any questions about the multimeter quiz? Because it's due in a couple days. Any question at all? One question that's come up twice today is regarding the resistance of these bulbs. Somebody asked, what should I get for the resistance? And they kind of vary. I mean, somebody got 0.9 ohms. I had someone here a little while ago, and I measured this one. It was like 2.5 ohms. So it's going to vary, so don't worry about it. Okay. If it's 100 ohms, well, I should say, if it's 100 ohms, I'd worry about it. That's not a good bulb.
You froze again, by the way.
Okay.
There it is. You moved. Right.
I think it's my computer. I don't think it's the internet anymore because the Wi-Fi here is pretty good. So anyway, if you got anything between anything between like 0.9 and 3 ohms for the resistance, that's okay. Oh, let me check the chat real quick here. Yeah, I'm doing time travel. So any concerns? Have you blown any fuses? And look, we know mistakes will happen. I mean, part of learning is to make mistakes. I expect people to make mistakes in the lab. I mean, if the fuse gets blown, the fuse gets blown. If you blow through, if you've gone through 2 fuses, don't worry about it. We have more fuses. You just got to come and get them. Okay, so don't be too concerned about that. Because you're not great at the number of fuses you're blown, but at some point you want to get good at making a measurement. So it's measuring current that's the issue, right? And measuring voltage and resistance is pretty straightforward. No questions then? Okay, so
I had a quick question on when you measured the voltage or the whatever the other term was, the potential difference.
Yeah.
So we're definitely measuring that off of the bulb, right? And we'll get a slightly lower reading than if we took it directly from the battery.
Yeah, it'll be slightly lower. Part of it is, well, part of it is that the multimeter's resistance is not ideally infinite.
I see.
That's part of it. But yeah, they won't necessarily be the same.
Okay, cool.
Okay.
Thank you.
Sure. Other questions?
I have a question.
Sure.
About like the lab we're supposed to be submitting on Sunday. And I was wondering, when we connect like the multimeter to measure current, do we connect it like on the positive end of like the battery or the after, like on the negative end? What I mean, let me show you like the video.
You're concerned about whether you put the positive. You're worried about. Oh, go ahead. Let me.
So like because the battery, like the negative end goes here, and like the positive usually goes here, right?
Yeah.
Like so when we're doing like the current measurement. We have like one bulb and like one battery here. So if like the positive end is here and the battery is here. So do we connect the multimeter between the positive end and the battery, or between the negative end and the negative end and the bulb? Sorry.
It really doesn't, in terms of measuring the current, it's really not going to make a difference. So you'll know you hooked it up backwards because you'll get a negative sign in the current, that's all. But it won't affect the current. So if let's say I'm going to draw my battery like this, and here's my bulb. If I put the multimeter like this is the plus end of the multimeter. So this is the red one, and this is the black one. One. Then when it reads, it'll give you a positive number. If you switch these around, so that this is negative and this is positive, then the multimeter will give you the current with the minus sign in front.
Oh, okay. I see that.
And that's not a problem. I mean,
right.
and it doesn't matter where you put this. If you put it here or here, I mean, it really doesn't matter.
Okay.
Okay.
All right. All right. Thank you.
Sure. Yeah, and same thing when you're measuring voltage. If you have the leads reversed, it's just going to tell you you have an issue, you have it backwards. You'll get a minus sign, but nothing will happen, and you're okay with that.
All right, thank you.
That's a good question, because I think a lot of people don't ask that question, and you don't have to worry about that. You just have to worry is if you hook the ammeter in parallel, then that would be bad. Then you'll blow a fuse.
Okay, thank you.
Sure.
So can I actually ask another question about the same thing? So if we need to keep it in series, but for my thing at least, for the multimeter, it's just prongs that I'm just sticking on something.
Yeah.
So if I'm just sticking that on the two open ends of the wire, one being leaded to the bulb and the other being led to the battery, it should keep that, that should be in series, correct? Sorry if I'm not making sense there.
Say that one more time, I'm sorry.
So with your diagram here, the positive end and the negative end are the two prongs that come off of the multimeter.
Yeah.
And those are just the ones that connect, they don't physically connect, I just have to hold them up to the wire to be able to get a reading.
Unless you use this one.
Okay, so those do plug in to the multimeter as well, correct?
Yeah, they'll plug into them. They'll be a little bit loose, but that'll work.
Okay, cool. I wasn't sure if they were for that because they were a little loose, but I see now. Thank you.
Yeah, sure. But either one's fine. Yeah, I actually don't like those leads. I'd rather have alligator clips so they hold it in place. They're all like that, though. Other questions? Okay, so our next lab is on Ohm's law. It's called Ohm's law and resistance, and you see it on the screen. So this will be the first lab where you actually write a formal report. And really from now on, almost all the labs, except maybe one, you have to write a formal report. And I'm giving you a long time to do it, and the reason why is because I want you to turn in a hard copy of the report. It's actually easier for me to grade the hard copy, something on paper. So you're going to print it out and turn in your printout. Then I can grade it. I think I can grade it a lot faster than if I have to grade it on Canvas. So you have all the way until October 29th to turn it in. And I know as human beings, we would like to do things to the last minute. But I highly recommend that you actually get this done at around maybe by the 15th or around there. Okay. You should be in a position where you're almost ready to turn it in around the October 15th, October 16th, in that time frame. Because on October 15th, 2 weeks from today, I'm going to introduce the next lab. The next
How
lab
long?
requires a lot of wiring. Well, no, actually some wiring. The procedure is actually easy, but you have a tremendous amount of analysis. It's really all air propagation. There's a tremendous amount of air propagation.
Professor,
Yeah.
how long does it take to write a formal lab report?
Well, I mean, how long did it take you in 205? I mean, it should be,
I don't know if I
it's
did
going to
in
vary,
205
right?
because I didn't take 205 at Sierra. I took it at a different school, so I don't know if I did a formal lab report when I took it. But
So what what I mean by formal is you're gonna type it up. I mean, at the school you went to, were they like handwritten?
it was more like because it was all on Zoom, so I think the professor just, if I remember correctly, the professor just would do the lab, and then essentially he would give us all the data, and then we would just, yeah, I guess it would be handwritten, yeah, but I don't know if there were specific, like for your class, are there specific like sections that we have to do? Because like I've taken chemistry where it's like you have to write the procedure, you have to write like the steps of the lab and all. Do we have to do all that, or is it just explaining what you did?
Most of it is documenting your results, doing derivations that are required. This slide doesn't require any derivations, but putting in any derivations, copying and pasting graphs into your lab report.
Okay, and then also so data, and then also like the calculations.
Yeah, and the analysis.
Okay.
So
all right.
basically, the document that you see on there, all you got to do is essentially fill in the blanks. But it sounds easy saying fill in the blanks, but there's actually quite a bit of work that you end up doing. This one's a little bit easier than the next one. The next one is a little bit more intense. So really what I'm talking about is I want you to type it up, right?
Yeah.
And
Make it more official.
so if you, and I know there's a couple of folks in this group that didn't, I guess, had the equivalent of 205 somewhere else. And so you need to be in contact with me regarding, my expectations. I thought I had on Canvas a sample lab report. And so it's not there. So I'm going to email you all a sample lab report. So for those of you who are new to Sierra College, you'll get to see what's expected. For those of you who are not new, you had 205 with Aviva. I pretty much have the same requirements. I probably add one or two, though. I tend to add one or two items, but I pretty much have the same requirements that she did. Okay. But yeah, those of you who did not have Physics 205 here at Sierra College, please be in contact with me about the lab reports, because I want to make sure that you understand the process, and I'm going to. I'd rather do it help work with you individually than spending a lot of time in class going through everything. But if there's something that you're not sure of, just stop me, okay, and just ask a question.
Would it be possible, like for the lab reports, to like email it ahead of time and ask if it's like up to standard, or is that? I know that's putting more work for you, so that's why I'm asking.
Well, are you able to come to class with a printed come on Mondays or Fridays with a printed version? It's faster. That's why.
Yeah.
Yeah.
I could. Yeah. Yeah.
Yeah. It's way faster that way.
That makes sense. Yeah. Okay.
And if you get started early, that's better, because then you can, you don't want to be rushing to at last minute. Yeah, I have no problem with you. Those of you guys who are new, ask me questions about the lab report. But if you're going to show me something, I'd rather do it in person. It's a lot easier. It's much faster, because otherwise, if a lot of students do that, it's on doing stuff like that online is just time consuming. Okay. So on the 15th, like next week, remember you guys have an exam, right? On the 15th, I'm going to introduce the next lab, which is on circuit analysis, and we'll be doing circuit analysis by that time. Again, it's to be a lab on another lab where you're practicing wiring circuits, and so you will be handing hard copies. Okay. By the way, don't forget you pick up your exam. I still have a bunch of them in Tyler's office, the RIA's office, across from my office. Okay. So you're on your way to finishing up the multimeter quiz. And you remember a little bit about Ohm's law. Remember Ohm's law? We can write it this way. R is delta V over I. Or you can write it as delta V is I times R. But if a material obeys Ohm's law, this ratio is constant independent of delta V. If you have a light bulb, this ratio is not constant as you vary V. So light bulb does not obey Ohm's law in the sense that this is a constant. If you make a graph, delta V here and I here, you're supposed to get a straight line if the material obeys Ohm's law. If you don't get a straight line, the material doesn't obey Ohm's law. But still, this equation is still true. It's just that this number changes. Okay. So you're going to be building some simple circuits, and you're going to be looking at Ohm's law, and you're going to be building circuits on something called a protoboard, or some people call it a breadboard. This came in your lab kit. You're going to be building your circuits on this device. Okay, so you see there's a bunch of holes in them, and inside here, inside the material, there's conductor, which is wired so that the holes are connected in a particular direction. And so in part one of the lab, you have to go along and figure out how the holes are connected. Okay, so you have to figure out how these holes are connected. So how are we going to do that? That's the question. Well, it turns out you can use a multimeter set on measuring ohms to do that. So what I'm going to take two random holes, and I want to see if they're electrically connected. So I put two wires into the breadboard or protoboard, and I'm going to actually use these wires to measure resistance because they have alligator clips. Okay, wrong side. They have alligator clips.
You're
So
frozen.
I'm frozen. Okay.
It just shows the breadboard in the corner.
Okay.
There it is.
So, yeah, my video capture software is in front of Zoom, so I can't tell sometimes. Okay, so you use these alligator clips. So I'm going to connect the alligator clips to those leads, to those wires. Like that. And then the other ends are going to go to the multimeter. So I can measure resistance. So notice that the multimeter reads a 1. In fact, if I put it in the highest scale, it reads 1 with a dot. That means a very high. Uh-oh, that wasn't good. I don't want to have a short. That means I have a very high resistance. So those two holes in the board are not connected to each other. Okay. So what I'm going to do is pick another pair. This pair and this one and this one. And you'll notice that it reads 0. That means that those holes are connected. And so what you want to do is find out which holes are connected to each other so that you can figure out how to wire your circuit. Now, it doesn't mean that you have to go through every single pair of holes to see how they're wired, because you're going to notice a pattern. Once you notice the pattern, you'll be done. And then what you can do when you're doing your lab report, you can actually go into Word. See if I can do this. And you can insert. Fortunately, I'm on 2 screens that are really far away. I can insert a line with the drawing tool. Sorry. My line doesn't show up very well. And I didn't draw it very well. So there's my line. To show how they're connected. Hold on a second. So I can do something like that, and that shows that, okay, those are all connected. Okay, so that's what you want to do in this exercise. And so you want to show how the holes are connected. That horizontal line that I drew says that all the holes in that row are connected together. Okay, so you want to go do something like that to indicate how they're connected. Questions on that? Let me check the chat. Okay, let me check the chat box real quick. Okay. So I want to reiterate, the fact, these multimeters can be used as a diagnostic tool. You can use it to test things. You can use it to see if things work, or you can use it to figure out why things aren't working. Let me give you an example. Suppose I have some electronic device, and all of a sudden it stops working, and I suspect the plug. Is there something wrong with my plug? I can take an ohm meter and measure the resistance between any pair of prongs on here. If I get 0 ohms, let's say between the ground, this is the grounding plug, and let's say this guy, probably means I have a short somewhere. Maybe something shorted inside the other end of the cable. Maybe something on the other end of the cable is shorted. Okay. If I have, now your plug looks like this. Let's say you have a cable, 2 prongs here, 2 2 prongs here, and in here, the cable, you have 2 wires. All right. There's 2 wires inside this cable. One's connected to this and one's connected to that. Okay. If I measure the resistance between these 2 prongs, if the resistance is infinite, that means that something's wrong inside my cable. Okay. If I measure the resistance between these 2 and I read 0, that means it's shorted. That's not good either. So you can use the multimeter to troubleshoot. One of the skills I want you to develop or start developing is the ability to troubleshoot things, because that's going to be an important skill no matter what you do. I mean, you're all in this physics class because you're either going to be an engineer, computer scientist, biologist, chemist, physicist. Okay? Maybe the exceptions, maybe the mathematicians. You're going to be troubleshooting things, troubleshooting something you're working on. And so you have to develop a problem-solving process, some sort of process to help figure out what's wrong. I guess in mathematics there is something like that too, but it's more in terms of finding your mistake in your the work you do on paper. One of the things that's not really emphasized in science labs is the troubleshooting skills. I mean, the first lab that you did, where you built the electrophorus and the electroscope, even though they look simple, you had to make sure that it worked. And so what you had to do is figure out what you had to do to make this thing work. As an engineer, you have a project, and it's not working. You got to figure out what went wrong. And there's usually not something you can Google or anything or ask anybody about that'll give you the answer directly. You have to actually develop a process for troubleshooting, figuring out what's wrong. If you're coding, same thing. Okay, so it's an important skill. It's an important skill I want you to develop, and I'm going to have you learn how to use these things, for example, to troubleshoot a circuit. Later on this semester, you're going to be building a motor. And it looks simple to build, but if you want it to operate optimally, you actually have to do some troubleshooting to make your motor work better. Okay, and so I'm gonna try to emphasize these skills in this lab. Okay. So part one, pretty straightforward. I'm sorry?
You're frozen for me, by the way.
Oh, again?
I don't know if that's for anyone else, though.
No, I was frozen. Thanks. So that's part one. Okay, it's pretty straightforward. So now in part two, you're going to be using this to build your first circuit on that board. And we're going to test Ohm's law. So you're going to take a variable power supply. The arrow means you can vary the power supply. Positive end power supply goes to a resistor. The other end of the resistor will go to the positive side of the ammeter. The negative side of the ammeter will go to the negative terminal of the power supply. That's your circuit. But also, you're also going to measure the voltage, or I should say, the PD, the potential difference, across the resistor. What does your power supply look like? This is your power supply. came with your kit. If it's brand new, it'll be in a box. If it's not brand new, it'll be in a bag. Okay, so this is just a power adapter. And there's like 7 settings on it, so we can actually get 7 data points for this part of the lab. You can either use a screwdriver to change the voltage, or you can use this device that came with the power supply, this guy. You just put it in here like so, and you twist. And that's going to allow you to change the voltage. So it's this guy that came in the kit. Okay? If you don't have that, just use a screwdriver, a flathead screwdriver. Okay? So you're going to be using this power supply to build your circuit. And what I've done is your power supply also comes with this guy. So this connects to your power supply, like so, it just fits in nicely. And then you insert a wire here and a wire here. You're going to insert 2 wires into this, and then you're going to tighten the screws at the top so the wires stay in place. And what I did to make things easier to work with, I taped this, basically this piece, right? I taped this piece onto the proto board so it doesn't move around. So all I need to do is plug this in. And then the other end, I put into an outlet, okay? This goes into the outlet, and then this gives me my power. Now, how do I know which one's positive and which one's my high voltage and which my neutral? I can take an ohm meter, put the ohm meter, one lead here, and then one at the center pin. Center pin looks like that. And if I get 0, then I know that that wire is connected to that center pin. That's your high voltage. Okay, if it doesn't work, then I know that's my low voltage. Okay? So you'll have this, you can attach it to your board, and then these wires then you can attach to your circuit. And you have 7 voltage settings. Now Tyler has created a video, and it's in the module for this lab on Canvas. So you'll see that there's a video on Canvas showing where Tyler is showing you all the different parts of the experiment, all the different pieces of equipment in the experiment. And so his video is specifically designed to show you the equipment, so he does a better job with the camera work than what I'm doing now, because I'm kind of doing it live. Okay? So please watch that video. It's only about 10 to 15 minutes. Okay, so you're going to wire this circuit, and you're going to measure voltage, the potential difference across the resistor, and the current. You'll get, I don't know, you'll get 7 data points. And you will do a curve fit to this data. So delta V on the vertical axis, I on the horizontal axis. And then switch these from the PowerPoint notes because the slope will give you the resistance directly. So the slope is going to be R. So those of you who took Physics 205 here, you use Cy Davis to make your graphs. And you did your curve fits. Okay? So I expect you to use Cy Davis or something reasonable. Don't use Excel. I know a couple of you probably used Excel to do curve fits. Don't use Excel because it's not going to work for all our labs. I have a document in the modules specifically geared to this program called Cy Davis. It's free. If you just Google Cy Davis, you'll find the website. And then you can go and download it onto your computer and install it. I'm going to try to find an old video. I think it's from my Physics A class where I talked about how to use Cy Davis. I'm going to have to go look for it. And maybe I'll put that in the modules or email you the link. Okay. If you don't want to use Cy Davis, you can use something else as long as it allows you to do curve fits. It gives you the results of the curve fits along with the uncertainties. Yeah, I should really write it down. Sorry about that. I'm sure there's other ones that are free. This is a free one. That's why I use it. The Windows version is in good shape. The Mac version is not, because when I use them, because I use the Mac version sometimes will just disappear from my computer and I have to reinstall it again. I don't know why it does that. That's in a beta version. That's why, I think. But the Windows version works fine. And somebody in the previous class mentioned a different one. And I got to go look at the chat. Try to remember. If that one works fine, then I'll use that one. So you're going to do a curve fit to your data. If the material obeys Ohm's law, you do want to fit to a line. And you have two possibilities. These two represents a fit to a line. But one of them should never be used. Guess which one?
MX plus B, I'm assuming?
Well, that's the one you want to use. Actually,
Oh.
this is the one
And
you
I'm going to
never,
guess Y equals AX.
Yeah, you never want to use that one. Why? Because you're forcing the data to go through you're forcing your results to go through the origin. That's why. So you should not use, you should never, and I mentioned this like every semester, but there's always somebody who actually uses this curve fit. Do not use this, use this. You're going to fit to this equation with your software. Okay? In Excel, it's called a linear regression. Right? Those of you who've used Excel before, they call that linear regression. The software then will give you the slope and the uncertainty in the slope. It'll give you the y-intercept and the uncertainty in the y-intercept. I need to see those values on your graph. I actually need to see the raw values that the computer spits out, that the software spits out on this graph. Because I need to see that you can interpret the results. I want to see that you can report everything to the correct number of decimal places. So I need to see that on the graph. And I will take off points if I don't see that on the graph.
So it's the rounded one that's on the graph, right? The after sig figs?
No, actually, I don't want the rounded one here. I want the original values
It's the
here.
unrounded raw? Okay.
Yeah, I want the unrounded raw, because what will happen is later on in the lab, it'll ask you to put it in, say, what is the slope and uncertainty? That's where you want to quote it to the correct number of decimal places. So let me show you the document real quick. Hopefully I don't freeze up. So this is part 2. I forgot to write the resistance value, but anyway. This is the data table. Pay attention to everything it says there. Watch the units. Okay? You're going to measure the resistance with the multimeter too. There's your data table. There's only 7 points. But when you get to part 4, I mean not part 4, the results section, this is where you're going to put in the slope and uncertainty to the correct number of decimal places. The reason why I want to see the raw result on the graph is so that I can see that you can interpret the results correctly. That make sense?
Is there?
Okay.
Did you scroll down past part 3 or right where it says part 3?
You want to go further down?
I just wanted to make sure it didn't freeze, so that's why I was.
Oh, okay.
asking.
Let me take a look. It froze. Because I was playing around with it, it froze, so. Okay, so again, where it says slope and
Okay.
uncertainty, that's where you want to write number 6
Yeah.
is. Okay.
All right, thanks.
All right, let me change the view on here. All right, so this has to be there. Of course, everything has got to be labeled. When I send you the sample lab report, you'll see that you'll have the axes labeled with the right units, and then you'll have a title in the graph. Okay. And then a lot of the information is actually in the syllabus. Now, you're going to have to use the resistor that's specified in the lab. And the resistor is 820 ohms. So in your kit, you do have a resistor that's 820 ohms. How do you know that the value of the resistor is 820 ohms? Well, what's the resistor look like? Well, they kind of look like this. They have a bunch of stripes on them. This is made out of carbon film. What is this used for? It's used for limiting a current in a circuit. It's used for maybe producing a voltage that you'd want for some device. And they're designed so that they obey Ohm's law. That's how they're designed. If you actually put too much current through them, if this dissipates too much energy per unit of time, you put too much power into this thing, it'll actually get hot, its resistance will change. So these have a power rating. We'll talk about that later. So you're going to be using those. And so how do you know which one is the 820 ohm resistor? That's the question. Well, those stripes that you saw are really a code. There was 4 stripes on there. We use resistors that have 4 stripes. There's some that have 5. We try to stay away from, I guess we try to avoid those, but we traditionally have used resistor with a 4-band code. The 4th band just tells you how precise that value is. So there's a code to the colors. Let me write down the different colors and what number they represent. There's black, brown, red, orange, yellow, green, blue, violet, gray, and white. So black is 0, 1, 2, 3, yellow's 4, green is 5, 6, 7, 8, 9. Okay, well, so what? Suppose I have a resistor. That has a color code where the first band is red, the first stripe is red. The second one is red, and I'm going to be consistent with the other classes I did today. The third one will be green. Now the fourth one is usually silver or gold. I don't have gold marker and I don't have silver marker. So the fourth band tells you how precise this value is. This is a nominal value. If you want a better value, you got to measure with the multimeter. Okay. So the fourth band tells you how precise it is. So if it's gold, then if the band is gold, then it's 5%. It's that value plus or minus 5%. If it's silver, it's that value plus or minus 10%. Okay. So red is 2 on that thing. So let me, the first band is the first number, the first digit. Second band is the second digit. And then the third band is the multiplier. It's 10 to a factor. So this is 2, 2, and then green is 5. 22 times 10 to the fifth. 22 times 10 to the fifth ohms are 2.2 million ohms. That's the value of that resistor. That's how that works. So first digit, second digit multiplier. And the green is the exponent on the 10 there. Questions on that?
That's for measuring the resistance, you said?
That's the value of the resistance based on the color code that you see on the resistor. So you're going to use on 820 ohm resistor. So the first digit is going to be the first one's going to be gray. So you're going to find a resistor where the first one's gray. Hopefully there's only one in the kit. Okay. So that'll give you a way to find out which resistor is which. You got to use the color code. Questions? All right, so you know how to get the resistor value, not the proper resistor. We've talked about how to graph everything. Now, one more thing about the graph, and every graph that you produce this semester. I'm going to have to erase this. You have a graph in your lab report. A lot of times people put a graph in their lab report and they say nothing about the graph. It's just sitting there. It's like, why in the world do you put a graph in your lab report if you don't say anything about it? Because this graph tells you a lot of information. It organizes your data. It shows the relationship between this quantity and that quantity. So what I want you to do for every graph you make this semester is you have to have a figure caption. Every graph has to have a figure caption. So your graph, underneath the graph, you should say, this is a graph of potential difference versus current for a resistor in a circuit. And then you can say that the data was fit to a line and the data fit the line very well. Or you can say the data did not fit the line very well, the curve, the theoretical equation very well. And maybe you can try to explain why. And you can also say this allowed us to obtain the value of the resistor. Tell me something you learned about, basically tell me something, some kind of physical thing that you learned about the graph, right? What does the graph tell you? Okay, what information does the graph tell you? I don't expect a long paragraph. I expect maybe 3 sentences, 4 sentences tops to convey the information I need. That shows you that you thought about the graph and the information you got out of it. Every graph is going to be like that. If you just say this is a graph of electric potential difference versus current, and you don't say anything else, you're going to lose points. I am pretty critical when I grade the lab reports, so if you have questions about your lab, your lab before you turn in, please don't hesitate to ask, okay? Questions? All right. Now, part 3, essentially the same circuit, except that I'm going to replace the resistor with a light bulb. Light bulb does not obey Ohm's law. Of course, this is still valid. For a light bulb, you're not going to get a straight line. It's going to be curved. You're going to have seven data points, and you're going to collect data for a light bulb. Now, the light bulbs that you used for the multimeter quiz will not work in this lab, because that's the first thing I tried when I was designing this lab when we went online. And I just smoked the bulb when I got to 6 volts. So I had to go around and find something that worked. And really what kind of worked is a landscaping bulb. These are landscaping bulbs you can find like at Home Depot or whatever. We got them from Amazon, so we can buy them in bulk, cheaper. Okay? And so you have 2 prongs to make the connections. Now the problem with the landscaping bulb is it does not fit into the board. So what you might need to do is to use electrical tape to tape wires to it so you can make electrical connections. Or if you're really having trouble, just come here and do this part over here. We have more wires with alligator clips on them. And the alligator clips, they're isolated. They work really nicely. Okay. So we have extra ones here, so if you want to do the lab...
again, by the way.
There it is. Okay. I'm okay now, right?
Yeah, you're good now.
Okay. Yeah, I don't know. My computer's acting weird. I think it's on its way out. So you see that these alligator clips would work nice. So if you want to come here during the week if you can email Tyler, just say you're interested in using, coming to do this part of the lab. Just go ask him. Okay? Or tell him, can I come? Now, of course, if it's on a Monday, I'll be here till 3:30, so you just show up. Okay? So that's going to be the one issue with the bulb. Okay. But anyway, you're going to collect 7 data points again. Voltage is a function of current. Really should be the other way around. But so you're going to make this graph. You're going to make it inside Davis. I don't know what function fits to that. So your goal is to figure out what best fits to your data. You can try different Kurt fits parameters. I'm frozen again. This is pretty bad. Today has been a bad day with this computer. You can try different curve fits. Here's some examples. Try those, see what works best. And then you can show all of them, or you can show me the one that works best. And in your figure caption, you can say, I tried this, this, and this, and the best one was the one you see in the graph. You don't have to obtain any curve fit parameters. So one of the things that's irritating with this lab is that there's always one student who will fit this to what? Guess what? They'll fit it to a straight line. Do not fit to a straight line. Okay. I'll write that down, but of course, those people who are not watching the video are probably not going to see that. Okay, so do not fit that to a line. You can choose another function. But notice that there's only 3 curve fitting parameters on each one of these. Remember, and X here is the current, Y is the voltage. There's only 3 curve fitting parameters. You don't want to have too many curve fitting parameters. I mean, if you want to, you're going to fit your results to a 94th degree polynomial. And you would get great results. But then you'd have to figure out what each one of the 95 curve fitting parameters physically mean. Okay, and you have no way of knowing when you have too many random parameters. So the less parameters you have, the better. So don't give me a curve fit with a ton of fitting parameters. I mean, these are good choices. Okay. And then, and when you look in the results section, it's going to ask you to interpret your results. It says, what are the conclusions? Just see if you can explain the results. I'm not looking for a right answer. I'm just looking for you to use your thought process. Okay, what are you thinking? I'm just trying to get you to think. Okay? Questions on this? Again, it's going to have a figure caption. All right, let's talk about the last part. And I'm going to scroll down to part 4. This is a fun circuit. In part 4, you're going to build a circuit that has a diode in it. And most of you have never seen a diode before, so let me show you what our diode looks like. I'm going to bring it up to the camera. I'm frozen again. Okay. The diode looks like this. It's having trouble focusing. I'll bring it back a little bit. It has a little bit of orange on it and a black band. Okay? Has a little bit of orange on it and a black band. I don't know how close I can get. Hopefully you guys can see that. A diode is a device that allows current to flow in one direction. It allows charge to flow in one direction. Schematically, we represent a diode like this. This basically indicates the direction the current move, the electrons move here. So if I put a high voltage here and a lower voltage here, current will go in that direction. Okay? Charge will flow in that direction. If I reverse the polarity, if I make this positive and this negative, if I put the positive side of the battery here, the negative side of the battery here, no charge will flow through the diode. Well, that's ideally. I mean, there's really a small amount that goes through. So we're going to use this in a circuit, and it'll be your most complicated circuit you're going to work with. There's actually two new items, that and a special type of resistor that's variable. It's called a potentiometer. So let me show you the potentiometer. In your lab kit, you have something. Oops, I'm going the wrong direction. That looks like this. It has 3 prongs on it and a dial. Okay? This is the potentiometer. And it's basically a resistor in which you can vary. So let me start by drawing the circuit. And when I get to the potentiometer, let me say some things about it. You're going to have a set power supply voltage of 12 volts. This resistor is really there to limit the amount of current in your circuit. This is where we get to the potentiometer. So what does this thing do? Well, let me kind of draw a little bit what it looks like. So there's the dial, and then this is the body, and there's 3 terminals that come out of this thing. And the wires go somewhere in here. This is a 1,000 ohm potentiometer. For sure, we just call it a pot. We call it that a 1K pot. And they vary. There's the real good ones. You can turn, the dial, you have to turn 10 times before you go from 0 to 1,000 ohms. This is only a 1-turn pot, so it's not an expensive pot, okay? It's not very sensitive. But you know, we were trying to save money with the lab kits, okay? So let's say I have a power supply, and I connect one wire of or battery, whatever you want to call it, or whatever you want to use, I mean. One end goes to this terminal, and the other end goes to this terminal. If you use the outer terminals and connect them to a battery, you're going to get the full 1,000 ohms from the potentiometer. You can turn the dial till you're blue in the face. It ain't going to change anything. It's 1,000 ohms. However, if you take this lead or this wire and connect it here to the middle one, now you have a variable resistor. The dial, if you change the dial, you can vary the resistance from 0 ohms to 1,000 ohms. That middle one is called a sweeper. And basically, this allows you to basically move this up or down. It basically, if this is the whole resistor, you're only sampling a portion of it by changing the dial. Resistance really depends on the length of a wire. So, you know, you can think of it as changing the length of the wire that's used as a resistor. You can also wire it this way. And again, you'll have a resistor that varies. But instead of going from 0 to 1,000, it'll go from 1,000 to 0. Basically, you're either using this resistor or this resistor. Okay? So basically, if you use these leads, you're using this part. If you're using these two leads, you're using this part. So we're going to be using these two, this part. I'm sorry, we're going to be using this part. Okay? So what we're going to do is we're going to have the middle lead on the potentiometer go to an ammeter. So let's say this is the positive side of the ammeter. The other side of the ammeter will go to the diode. And then this will go to the common, the negative side of the power supply. And then you're going to measure the voltage here. So you're going to measure the voltage across the diode and the current through the ammeter. And you're going to collect about 28 data points. You really need to collect a lot of data points for this. Because we know the relationship between current and voltage for the diode. Let me scroll down. You can tell you have a big data table. Okay. So you want to collect like 26 to 28 data points. The graph will look like this. In this particular case, we're going to put I on the vertical axis and delta V, the electrical potential difference across the diode here on the horizontal axis. We're plotting current versus voltage. And the graph will kind of look like this. The data will pretty much be exponential. You're going to fit to an equation inside Davis, and you're going to have to define the equation. You won't be able to do this with Excel at all. You're going to fit to an equation that looks like that. Now, this is the potential difference across the diode. V sub t is K sub B times the temperature divided by the charge on the electron, the magnitude of the charge on the electron. K sub B is called Boltzmann's constant. If you had 215, you've seen Boltzmann's constant, or chemistry, I guess. It's 1.38 times 10 to the minus 23rd joules per Kelvin. T is a temperature in Kelvin. And this is 1.602 times 10 to the minus 19 coulombs. At room temperature, this number is like 0.02 something, like 0.026 or 0.025 at room temperature. How are you going to measure temperature? How are you going to measure the temperature in your room? There's no thermometer in the kit. Well, if you don't have a thermometer available, then the place you live should have a thermostat. And on the thermostat, the thermostat will read the temperature. If the thermostat's set to 70 degrees, then that's probably the temperature of the room. Okay? Although a thermostat might also have the temperature of the room in addition to the thermostat. So use your thermostat, thing to control the temperature of your room, to estimate the temperature. Now you need a temperature in Kelvin. And the temperature in Kelvin is equal to 273.15 plus the temperature in Celsius. By the way, if you end up doing this experiment here because you want some help, we have thermometers here. So, like our lab S107, there's thermometers. There's a big thermometer on the wall. And you can use that if you want to do that. But if you do it at home, then you can use a thermostat reading if you don't have a thermometer. So that's what V sub T, and N is we're going to use it as a fitting parameter. And it's a number between 1 and 2, basically. So you're going to define a curve fit where this is a fitting parameter and that's a fitting parameter. And the next time we meet, I'm going to say a few more things about the lab. So it's very difficult. When I teach this lab online, I actually have to go through a lot more details because of the lack of interaction between you and I. And so it is actually much more difficult to talk about this lab online because I have to go through everything. I will have a few more things to say next time. There's actually one more thing you have to do, but I don't have time to talk about it today. I'll talk about it in 2 weeks. So you're going to do this curve fit to this data. I need to talk about how you're going to collect the data because it's important. This diode, once current starts to go through the diode, the maximum voltage drop across the diode could be as little as 0.2 volts or as much as 0.8 volts. It just depends on the diode type. What will happen is when you set this up and you have this turned all the way down, as you rotate the dial on the potentiometer, your goal is you rotate the dial here, you're going to be changing these guys. As you rotate the dial, for a while you won't get any current. Then all of a sudden, as you turn it real slow, the current will jump up. For a very small change in voltage, you'll see a big change here. That tells me you're in this part of the graph. This thing is an exponential growth. There's no minus sign here, it's a plus sign. So this thing is going to skyrocket. And so you want to play around with the potentiometer to see how these are related to each other. How fast this changes when this changes. When does this thing start going up? when is this essentially what you say? It's turned on. When does it start conducting electricity? Okay, because once it starts conducting electricity, the current will just skyrocket. The current will be in milliamps, but the current will skyrocket. Okay, you can have this change by 0.01. This current will double. So it's very sensitive. The A is the potentiometer. No, the A is the ammeter. This thing here is the potentiometer. That is this thing. So you see the outer terminals on here? The outer ones? That's this guy and this guy. The middle one is this guy. Okay?
What does it connect to? What's that black circle on the bottom that everything connects to? Is that just the cable or the
Which
wire?
which black circle on the bottom?
So it connects to the potentiometer at the top, right? On the plus. And then down
This?
below that.
This is the ammeter.
Okay. Then
That's the
that arrow thing is on the right is the diode, right?
This is the diode. This is the voltmeter.
Okay. And then what does it connect to, the voltmeter and the diode?
What is connected to the voltmeter and the diode?
Where do they connect? Where do they end?
Well, to here, right?
Well, but on the other side.
Here, let me get rid of the voltmeter. All right, this is the circuit you want to build, right?
Mm-hmm.
So you have your power supply here, your resistor that emits current. This is the potentiometer. That's the
Okay.
ammeter. This is the diode. And then I will connect a voltmeter to measure voltage. I'm not sure I'm understanding.
Well, just on the bottom line.
Oh, this?
So you get, yeah. What does that connect to? Is that just the wire of
So
the
this is,
circuit?
yeah, this is a
or-
wire. So these are all wires that connect to the negative side of the battery.
Okay, and then you connect the wire to the diode, the voltmeter, and the potentiometer.
Yeah, these are all in common.
Okay, all right, okay.
Okay, they all.
I wasn't sure
line
if
up-
the black dot meant something or not. So
Oh no, yeah, these are just to say that these are a junction,
okay,
and these go to basically that common point.
all right.
Okay,
Thank you. Sorry about that.
that's okay. And I made I'm sorry, I made my picture sloppy. I made it very sloppy.
I have another question.
Sure.
So we have, you have the ammeter and the voltmeter. Are we using the multimeter to measure both?
Yeah. So here's the problem. You only have one, right?
Yeah, that's a question.
Okay. So you're supposed to have two in your kit. So one of the multimeters came late.
Okay.
So you need a second one.
Oh.
So I already gave 3 of them out today because 3 students came and asked me questions. So as soon as I saw them, I said, here, take one of these. I really was supposed to have given them at the first exam, and I didn't.
Okay.
But if you come by Monday, I can give you one.
All
When you
right.
come and take the exam on Friday, everybody will get one.
All right.
Okay? So
Okay.
if you do part 1 for part 1 and part 2, you can do it with just one, because in part 1 you can take the ammeter out of the circuit and then use it as a voltmeter. But it would be horrendous to do this lab with 28 data points where you're just switching it all the time.
Yeah.
So you're going to need both of them. So if you're going to
Okay.
if you're going to work on it next week, stop by Monday and pick it up, okay? Or I mean,
Sure.
you'll get it by Friday. By Friday, everyone's going to have one because I'm assuming everyone's going to come take a test.
Okay.
Okay? So that's a good question.
Thank you.
Yeah, you do. You do need the two of them. I apologize for you didn't get it right away and that's because there was a delay in us getting them. Okay. So the maximum here is going to be, typically it's around 0.6 to 0.8. There's some diodes that only turn on at 0.2 volts, but so this thing is going to rise steeply. And so you want to take a lot of data points. You want to take 28 data points. I mean, you might only need to change this by 0.01 volts. So to do that, you got to turn the dial ever so slightly so that the voltage changes by 0.01 volts. And then this thing will double in some cases.
You froze again, by the way.
Okay. So you need to play, before you collect data, you need to play around with the potentiometer. See how these vary as you vary the potentiometer. You'll notice that once it starts turning on, once the current starts flowing, that just a small tweak changes everything by a lot. And if you're going to get a good curve fit, you need to be able to pinpoint your data here. You need a lot of data points here. Anytime you have a data where you have a curve in the graph, you gotta get a lot of points around the curve if you want to get a good curve fit. Okay. Yeah, the arrow thing's a diode. Yeah, like I said, this is the symbol for the diode. This is the higher side, this is the lower side. So it conducts in that direction if this is the higher side and this is the lower side. If you reverse it, no current, no charge flows. Well, a little bit does. And you're going to try to measure that in the last part. Questions?
I have another question.
Sure.
On the potentiometer, what side, like what prong is connected to like the ammeter, like the middle one?
This is the middle one.
Mm-hmm.
And these are the outer ones.
Okay.
Okay.
So
the middle one's the slider.
Okay.
And that allows you to vary the resistance. If you just use the outer ones, you get the full resistance.
Okay, so the outer ones go just on the circuit, and then the middle one is connected to the ammeter?
Yes.
Okay.
Yeah, this thing is unusual, so it takes a while to get used to it.
Okay.
Okay.
Yeah.
And once you get used to it, it's not a big deal. And what's nice about this is that it does fit into your board. So it does fit into the board. The only thing that doesn't fit into the board is that light bulb. Okay? So that's what's nice about this. Other questions? So go ahead and finish this up this weekend. And then at some point, and you can do this, what's nice about the various parts of the lab, you can do, for example, part 1 and part 2 one day. Because part 1 takes very little time. Part 2 takes very little time. Part 3 takes very little time. Part 4 takes time. Okay? But there's not a lot of analysis other than making graphs. You'll see that the analysis isn't too in depth. Just to get you familiar with Ohm's law and how to wire things and how some elements in a circuit behave. Diodes is a very unusual thing. And we're not going to go into the theoretical aspects of how a diode works anyway. You'll learn that in some other class. All right, if you folks don't have any more questions, I'm going to end it here. You all have a good weekend.
Thank you.
Thanks, Professor.
You're welcome. You're welcome, everybody.